Hello everyone. So in continuation of the yesterday lecture, today Dr. Sarkar will speak about some more and interesting results of real analysis. So I request to Dr. Sarkar, please start the lecture.
Okay, thank you, Dr. Gupta. Okay, so the screen is visible now.
Yes.
Okay, so what I wanted to do is Lagrange's multiplier, but I had a change of plan because usually this method of Lagrange's multiplier looks like always Hogwartish to me. It's kind of a magic. So thought in case there is a low dimensional proof for the method, and usually that involves something called implicit function theorem. So let's start talking about the two important results which you usually encounter whenever you look at multivariable calculus. Without this two, you cannot do multivariable calculus. So the first one is I'm going to kind of sketch it without giving much proof, and I couldn't make many examples today. So let's just try to focus on what these means. So the first one is inverse function theorem. So instead of talking about the multivariable part, let's try to give a simple example of the real variable case, how it goes. So in the real variable case, let's take a function from R to R. And you assume this is of class C1, and you know what this means so by now. So it means its derivative exists and the derivative is continuous. And let's assume that the derivative does not vanish at some point, then I can invert f in a neighborhood of that point. So this is basically the idea, and not just an inverse. Of course, inverse does not give too much information, but the inverse, if you just look at, it also turns out to be a function of class C1. Okay, so there are few problems over here in the proof is kind of a bit sketchy. If I'm writing something like fi, so I have to make sure this is an open set, which is kind of implicitly understood over here. If I explain you the proof of the multivariable case, you will see that this is kind of part of the proof itself. Okay, so how does the proof in the calculus go? So you start with a point where the function does not vanish, and because the function is continuous at that point, it is non-vanishing at some interval around this. This comes from the definition of continuity, and even you can say more just by this epsilon delta definition of continuity. You can say that the function doesn't change sign also in this interval. So if the function changes sign, obviously by intermediate value theorem, you can get a point in that interval necessarily, so that where the derivative should vanish. So here, actually, the sign of this is also kind of preserved in a sense. If you take, let's say, mod of f prime a to be your epsilon, and just cut it into half, take the half of it, and then try the epsilon delta definition, you will see that the function value in this interval is always bigger than mod of f prime a by 2. So automatically it means it's kind of positive if it's positive, or well, I mean, if f prime is positive, it is doable. If f prime is negative, you take the other inequality of the epsilon delta definition. Okay, so it stays non-zero in this interval. So I want to show that the function is injective on this interval. So this is also kind of almost immediate from mean value theorem. So if this is not true, I should be able to find out 2 points in this interval. I don't care too much where exactly it stays or how the interval look like. I can always take the interval to be open, so that's there enough necessary over here. And let's say I have ft1, ft2 coincide. So if I just assume this is not true, then this would happen. But from mean value theorem, I can just write ft2 minus ft1 as these factors t2 minus t1 interval length times some derivative, where the derivative is computed at some point in between, in some point c in between t1 and t2. But because of this reason, t2 minus t1 is strictly positive, so the only possible choice of this equation should be f prime c should be vanishing. But c is coming out of the interval where I already know the function does not vanish. So this would contradict whatever we have started with. Now, if this is a case, if this is injective on this interval, I can simply define the inverse g on fi just by writing down g defined at the point fx to be x. Okay, and that serves well. I mean, I can easily see that these two functions are inverse of each other. There is no problem with that. Now, out of this equation, if you want to prove that g is differentiable and the derivative is continuous, so the only problem a priori is you cannot use the chain rule directly because you do not know whether g is differentiable. The chain rule says if f is differentiable at x, g is differentiable at fx, then I will be able to apply chain rule. Okay, so this should be kind of done a bit directly, and this is where the proof get little sketchy because I need to know how fi look like. Again, to invoke the fact that I can shrink my interval I a little more so that if I can be looking like an interval, so this requires a little bit of work, which I'm kind of skipping over here. It's a bit cheating. I'm sorry about this, but you can try to figure out the more details. This is not so difficult. For instance, if you see that there is a close end of the interval fi, so first of all, fi cannot be a single point, so there has to be points. And because I is connected, I can take a open interval I. If I is connected, then fi should be a connected interval. So the only connected interval available in the real line, you already know their description. And if there is a close end around that point, what you can do is that you can prove that there has to be a value where the equality ft1 equal to ft2 happens around the end. So by doing all these tricks, what you can do is that you can further shorten this interval I so that your fi actually look like an open interval. Again, as I said, you'll see this in the more general case that fi being open is kind of automatic from one of the propositions. Okay, but whatever this is, if I want to find out the compute the g prime fx, how it looks like, so first of all, it should exist. For this, there is a direct check. I should write some y equal to fx and I try to test a limit like this. And again, to do this, I have to further write down y plus h for some h small enough so that this comes within this image. Otherwise, I won't be able to write g of y plus h. So if that happens, then this top line, whatever this is, this turns out to be x prime minus x. See over here, my g of y is x and g of y plus h is x prime. Okay, so g of y plus h is x prime. Okay, now then in that case, h is turns out to be this fx prime minus fx. So these limit actually become x prime minus x divided by, in the denominator, fx prime minus fx. And then I can use again the mean value theorem, writing down something like x prime minus x times f prime c1 for some c1 in between x and x prime. Now, again, this is a bit little intuitive. As my h approaches 0, this is where you would need fi to be an interval. As h approaches 0, then this x prime slowly try to converge to x. And therefore, it forces your c1 to converge to x. So this quantity, which is in the denominator, and of course x prime minus x is already in the numerator, so that would cancel. So this turns out to be this limit of something 1 upon f prime c1. Now c1 converges to x, and I know already f prime is continuous. So then this 1 by f prime c1 should converge to 1 by f prime x. Again, there you're using f prime x is non-zero. So therefore, the derivative would exist at fx. The g prime fx derivative exists, and it is equal to 1 by f prime at x. And then what you simply would need to assure over here is that this function is also continuous 1 by f prime x, because f prime x is continuous and f prime x does not vanish. So this immediately proves what you are looking for. So I can invert at one point where the function does not vanish. Okay. So what should be a first of all, what should be a multi-dimensional analog of this? So this particular thing R2R, so in a sense the dimension of both the real spaces are the same. That plays a significant role over here. And what you have noticed earlier, the derivative in general is replaced by a linear map. So if the dimensions are unequal, I won't be able to interpret this in higher dimension. And the most efficient way of interpreting this in the higher dimension is that just saying that the linear map I am looking at from Rn to Rn should be invertible. Okay, so this is also as a special case. It makes sense for calculus, because in the from Rn to, if you try to descend down to R, then the linear map is given by this particular coefficient. Remember, all linear maps from R to R, because it passes through origin, should look like some constant times x. So that constant should be your f prime a. So therefore, the determinant of that linear map should be your constant itself. So it makes sense to talk about the determinant of that particular function and assure that this is non-vanishing, and then you can try to invert around that. Okay, here, of course, if I just drop this continuity, this particular theorem in calculus also fails. So this example I have taken, I've kind of stolen it from Wikipedia. So if you try to intuitively kind of create a function like this, the most of the time it gives you something unpleasant. For instance, if I want to find out a function f which is differentiable but the derivative is not continuous, what I should look forward to is start with a non-continuous function and try to integrate to make sure that the function is differentiable. But the most common discontinuous functions which come to our mind are just kind of step functions. For instance, if you take the step function on the positive part of the real axis being +1, negative part of the real axis being -1, we integrate that with the constant coefficient 0, then it turns out to be the function mod x. And mod x is already continuous. So I can't do that trick over here. So here is an example, that the reason being that example I'll explain you. So first of all, you already know that there is a specific behavior of the function x sine 1 by x. It oscillates too much, even in the very close proximity of origin. So I basically want the function, whatever I'm looking at f, should not be injective. If I can violate the injectivity around the origin, I should be able to violate my condition, uh, the conclusion of this theorem without this differentiability. Yeah, sorry, with the differentiability or non-continuity. But x sine 1 by x oscillates too much in a sense that the derivative around origin, so there should be a, it often, in the any neighborhood of origin, it always reaches +1 and -1 very often. So therefore, the invertibility of f is invalid over there. So if it oscillates too much, if the derivative reaches at the derivative reaches at the extrema, which is 0. So for instance, in this function, you can see that around this corner over here, the derivative vanish. The derivative vanish just by seeking out something like Rolle's theorem. You can easily find 2 points very close enough whose values are the same. You can actually draw a straight line, horizontal straight line, which passes through two consecutive points which give the same values. So this is usually the trick, but there is a danger if I just use x sine 1 by x, because the moment you differentiate, it starts becoming sine 1 by x, because there is one component cos 1 by x which oscillates too much. Okay, so this is what I don't want. I want that part also to vanish. So therefore I put a quadratic part over there, so to make sure there is a 4x sine 1 by x which already vanishes. This minus 2 cos 1 by x will make sure that the function attains all possible +1 and -1 values in the close proximity of origin, and this one therefore would not create a problem. So now let's look at this function. If I try to take this particular sequence, for instance, 1 by 2 and pi, so at this sequence, the second part would already vanish because it's sine. Okay, and then I would not have to bother about what x is. Now if I just try to plug into the cosine part, I get a I get a -1 over there, I guess. So if it's 0, no, I get a +1 over there. So cos of 2 and pi is +1. Therefore, the function value would be -1 over there. Okay. So the derivative at this sequence is simply just -1. So therefore, the limit is -1, and it's not equal to the derivative at 0. And obviously that means that 1 by 2 and pi converges to 0, but the derivative does not respect this limit. So therefore derivative cannot be continuous. Okay, so this gives you an example of a function the derivative is not continuous. And again, the oscillation in the picture, what you see, most often it reaches the derivative 0. There is a maxima, local maxima at some point, then it drops down and again reaches a local minima and then goes up. And this oscillation, this is kind of very frequent, although this kind of looks like a straight line around the origin, but this is not the case. Even if you try to zoom around the origin, the oscillation keeps on happening at the close proximity of the 0, 0. So therefore, there is no way I can make function f invert at any given interval around origin. Yeah, because there is always will be I can always put a very small enough height, so that if I just draw a horizontal line with that height, there should be two consecutive points where the function actually value are equal. So this is what is exactly happening around this maxima, and same around this minima. Okay, so this gives a kind of a counter example. Failing this derivative being continuous, there is no hope of getting an inverse. So let's try to see how do I generalize this to higher dimension. So there are two key lemmas. One we'll try to apply to achieve this. So let's come back to this one a little later. So inverse function theorem, again, the statement should be very clear now. What we expect? We expect, okay, so we start from an open subset and assume that the function is of class Ck, and take a point where the function, instead of non-vanishing, which doesn't make sense, the linear map is non-singular. The derivative of f at a is non-singular. Then it says that I should be able to find an open neighborhood of that point where the function is invertible and its inverse is also of class Ck. Okay, and invertible in a sense, the function has to be injective in that neighborhood. Okay, so the proof is basically two-line proof, but there is a lot of preparation required, and I'm not going to do this because this is kind of a little too long for an 1 hour lecture. I think it should take at least 30 minutes to go through the details. So there are two key steps. The first step says that if you have the same scenario with assumption that the function f is just of C1 and the derivative non-singular, then there should be a small enough open neighborhood where the function actually look like this. So the norm of fx1 minus, so there is a typo here, norm of fx1 minus fx2 is greater than equal to k times norm of x1 minus x2. And this more or less tells you that if you manage to invert, that the function is bound to be continuous. Because if I just write fx1 equal to y1, fx2 equal to y2, then x2 turns out to be gy1 y2, and this is kind of a Lipschitz condition for that inverse. Okay, so immediately you will conclude that, okay, if I manage to invert, then the inverse will be continuous. So this proposition just makes sure of the second step. Okay, so then the other step is, if you take again an open set and take a function of class Ck from A to Rn, then if we assume the function is injective, by the way, that is not going to be given, and if the determinant at some point is non-zero for all x in that neighborhood, so this is my A, then your FA turns out to be open subset, and its inverse is of class Ck. Okay, so this step actually is more or less the proof of inverse function theorem. So this is a major step, but with bare hand try to prove an image of a function being an open subset in Rn is a tedious task. So for real line, what you have seen is that I was trying to argue that if I have an open interval, image of this open interval need not look like an open interval, but I can further shorten it down to make sure that it looks like so. Otherwise, it will fail to be injective around that point. Okay, so this trick actually required a little bit of higher dimensional analogs where a lot of techniques you need, and this is the most lengthy part of this proof, inverse function theorem. Okay, so now if we assume this too, again the proof of inverse function theorem is just a two-line proof. You start with because this determinant fa is non-zero, non-vanishing, so around that I should be able to find a neighborhood where the function is non-vanishing. Okay, so yeah, so the proposition 1.3, which you see over here, it takes care of this injectivity. So this is what is spoke of over here. There exists an open set u1 of a where the function f start behaving like an injective function. Now I got an injective function, but I still don't know how to invert this function. So my df is continuous now and this is non-zero. So the second part, uh, I mean the second proposition, this takes care of it. So therefore I should be able to find an u2 where the function derivative of the function does not vanish, I mean non-singular, at all these neighborhood points. And then if I take the intersection of these two, you get two key things because that satisfies the first property and the second property both. The first one said the function is injective and the second one says the function does not vanish. Now again you give a look on this proposition 2. If the function does not vanish on an open set and it is of class ck and yeah, it is of class ck and the function is injective, yeah, this is one of the requirement, then I end up getting the I end up getting that if f of u1 intersection u2 turns out to be an open set, and this on this particular open set you can invert the function which is g. So this is essentially more or less a proof of inverse function theorem. Okay, any question? Am I audible by the way?
I think in proposition 1.3 there should be less than or equal to in place of greater than or equal to.
No, actually, okay. So there is a, I think that this is not a problem. See, if we make it less than equal to this, then you won't be able to conclude immediately that your G is continuous. Okay, so yeah, I think this is correct. So there is no problem. Let's see, I kind of didn't give much thought on the proof. Yeah, I think this is correct. Yeah, so it required a little bit of trick, but yeah, so I don't have an immediate hint how should it be, how can I make it. So it's just a bit of jugglery around triangle inequality. No, the statement is correct. I actually verified that. What I fail to see is that immediately proving that this is injective. I think this is where it's confusing, right? So that's where you have to work a little bit. Yeah. Okay, so let me not spend time on this. Yeah, the inequality is correct, but how to get derive this second line that f is injective out of it, it takes a little while. So I think, oh yeah, so that comes from, yeah, that is immediate, right? So for instance, if you take fx1 and fx2 are same, then this vanishes. Then therefore, because k is positive, this forces this norm of x1 minus x2 should vanish. Therefore, x1 should be equal to x2. Yeah, so this is injective is kind of immediate. You need this one because this one forces the inequality. If you put it less than equal, you won't be able to guarantee that this part is equal to 0. Suppose I start with the fact that norm of fx1 minus fx2 is 0, then you won't be able to guarantee that norm of x1 minus x2 is 0. So yeah, so inequality is correct. So there is just a typo, this should be x2 over here. Is that fine?
Okay.
Okay, so let's come to example where we show that this invertibility is not global. So for instance, you take the usual rotation map, okay, xy maps to x cos y, x sin y. So you stick to the interval, the box 0, 1 on the x-axis and 0 to 2 pi on the y-axis. So to make sure, what you end up getting is a nice circle of radius r, and these color codes basically give an idea in which direction this map is rotating. This is the counterclockwise. The red one comes first, then the pink one is the second quadrant, and if I try to, instead of looking at the third quadrant, if I just try to push B around 2 pi, it try to get pushed towards these x-axis from the negative side. Okay, so you see here the function is not vanishing. So if you try to stick to B positive, then the determinant is this, simply this one, and the determinant of this is simply A. Yeah, so determinant of this is simply A. So if I make sure that my A is positive, so in that case, that the function does not is not singular. DF is non-singular. Okay. Now let's stick to the case B equal to B is greater than 0, because I want to make sure everything goes right. So if B is positive and above these cube and the segment 0, 1, then slowly try to fill up this circle from inside, and then if you make sure your B is less than equal to 2 pi, remember I am taking a open segment. So this cube, whatever you are looking at 0, 1 cross 0 B, where I am taking open intervals. So if you make sure, even if B equal to 2 pi, the last line, end line, which is 2 pi, will be missing. So I won't be able to reach that point where it violates the injectivity. The moment you include 2 pi, that is, you take a B greater than 2 pi, so that there are available points where you can compute the top line 2 pi. Then where it started with 0, 1 segment, and this the top line segment, that both of them goes to the identical image. So therefore it fails to be injective at that. So although even in this case around 2 pi, the derivative is still positive. Okay, so this one says, sorry, the determinant of the derivative is still non-zero. So this one says, even if I assure that the determinant does not vanish around a point, and if I go a little far away, so in this case I was trying to stick to somewhere at least in the red, let's say in the red region or in the pink region, whichever you choose. So if you go far away from there, the function might start becoming non-injective. So there is no way to get an inverse again. Okay, so let's come to now, how do we use this to prove the implicit function theorem? So there is an application of this which we are going to use. Okay, so you need some kind of notations. So if you have a function from Rn to Rm or some portion of Rn to Rm, you look at the components and remember this df. We have actually linear map, and I'm trying to write down mat of df being the matrix corresponding to this. So this is just a bit of different notation I'm trying to use just to make sure everything is nicely written down or expressed. So the matrix is often denoted like this. I'll write del of the component function f1 to fm with respect to del of the variables x1 to xm. The reason being, I might try to think of not taking all possible component functions, select some of them, and not all variables, select some of them. So what I end up getting is certain rows and columns of this full matrix mat of df. Okay, so that I might choose. So instead I take I1 to ipth indices for the functions and j1 to jqth index for the variables. Then this particular notation would represent the matrix given by choosing the I1th up to ipth rows and j1th up to jqth columns. Okay, so this is the minor corresponding to that particular pair of selection of indices. Okay, so this notation is going to be useful. So let's show some example over here. So let's take a simple example. You take the function from r power little r plus n to r power n. So what you would do is that ignore the first r variables and map these last n variables identically to Rn. Okay, so in short, I'm just writing fxy equal to y. So in that case, the component functions are just looking like this. If ixy is yi, and there are only n of them which is available. I is from 1 to n. Now I need to compute the dj of fi. So remember, dj fi means it's an entry for ith row and jth column. So dj means I'm looking at jth column, and let's say j equal to 1. So this is the first column. That means I'm looking at differentiating with respect to the variable x1. So if I'm differentiating with respect to x1, these component functions, they all vanish. So therefore, first k columns of these matrix would vanish. Okay, and then beyond that point, only if there is a match of j looking like r plus I, I'll be able to get 1. And other than that, I end up getting again the differentiability giving me 0 over here. So this del f del y I'll be denoting. So here x would mean the component x1, x2, xr variables. So del f, if you partially differentiate in this particular sense with respect to only x1, x2, xn, you get the 0th submatrix, 0 submatrix of size n cross k. And if you partially differentiate with respect to the y variables, you get an identity matrix. It's actually a slanted identity up to by this R unit, because this is not, well, the first R columns are already 0. Okay, so this is trying to explain you that the little notation I'll be adopting over here. So this will be used throughout in the next proof of implicit function theorem. Okay, so what does the implicit function theorem says? Again, the setting is the same. You take a open subset of r power some dimension r plus n, and take r power n on the right, and assume this is of class ck. Now what you want is, you don't want to kind of invert the function, because that is not possible, because the dimension won't match. The invert would exist if the dimension of these real spaces are the same, at least. Okay, so what you want is, you want some kind of coordinate wise inverse. So what is meaning by that? So you start with a point where the function vanish, but its derivative with respect to the y coordinates are computed at this point is non-singular. Okay, so then it says that the function should look like the domain points of the function on some kind of neighborhood. It should look like x comma gx, where gx are kind of supplied from some neighborhood which we are going to construct, and this x would be coming from a neighborhood of a. So this is the first coordinate of this. So there is a neighborhood of a inside rk. Remember, a comes from r, so there is again a typo, this should be r. Okay, so b is contained in capital R power little r, and I have a unique function which is of class ck, which takes my a to b, and which looks like locally x comma gx. And if I apply my function over there, I end up getting the 0 value. So this kind of should be thought of as, you have a equation f of a comma b 0, and I have the condition given by some kind of non-singularity, and then it makes sure that this equation is not solely depends on that particular discrete point, but on some kind of neighborhood of that. So this f of xgx equal to 0 can be solved in some neighborhood. Okay, so let's try to look a little bit more on the proof, and then these lines would be more and more clear what and how do they look like. So the main plan is to use the inverse function theorem, and if I want to use the inverse function theorem, I need the dimensions to match. So on the right side I have a r power n. So what I'll do is the simply take a function which takes the value xy to x comma fxy. So then it turns out to be rightly at place with r to the power r plus n. So if I do this, then I can easily see that the component function for the first little r many variables are just xi, and the remaining ones are my fi's with this extra factor r over here. Okay, so this is just the coordinates I'm looking at, and therefore because of this I can easily compute the values of the entries of the matrix of df. The first few entries will, again, the first r by r entries will look like the identity because it is the I goes to xi, and then in the column below I'll end up differentiating this with respect to, sorry, so what I have to do is yeah, so I have to compute, yeah, so here I still look at the jth column, so I just fix the column. So with respect to x, yeah, I'm trying to differentiate, and if I increase, yeah, sorry, yeah, now it's clear. So if the I just become more than r plus 1, more than equal to r plus 1, this particular entry will come del f del x, because these columns are contributed by various rows. Each of these rows, the first r rows are from here, the next n rows are from here. So I'll have del f del x over here. Again, if I try to do it, differentiate fi xy with respect to the y variables, I'll end up getting zero matrix. And then if I differentiate my fi xy with respect to y variables, I'll get that del f del y. Okay, so this expression is very crucial, and this is already immediate from these equations. Okay, next what I'm going to do is that I'm going to use the inverse function theorem. So what you need for that is the how do the determinant look like over there. So determinant of df is easily seen to be determinant of just this corner factor del f del y. Yeah, so this is just the block multiplication of this two. So this is matrix multiplication. If you just put it in a block like this, it looks like product of the determinant of the top one and the diagonal two, and subtract the, yeah, I actually it's not, yeah, it looks like the product of these two, and if there is a zero over here, then it vanishes. Okay, so in case my r and n were equal, this were I could have proved that it's exactly the block multiplication of the determinants as it happened by 2 by 2 matrices. But because of these odd size, it is actually not so. It will take a little bit of effort to prove that determinant of this is like this. You can just try to prove it by expanding through the first rows. Yeah, so the first row would vanish, and then 1 times the remaining ones. So this part essentially will not play a role. Okay, so let's see, start now with the fact that this is the determinant, and this does not vanish at 0 because I have already given that this det of del f del y at the point B does not vanish, right? Sorry, determinant of del f del y at the point AB does not vanish. So this one turns out to be determinant of that at this point, which does not vanish. And then I have FAB goes to A0. This just comes from my definition, because FAB, if computed at AB is 0. This is also part of my hypothesis over here. Okay, so I can manage to apply inverse function theorem. It's very cool now. So you can always restrict your attention to some open set, open neighborhood of AB, where AB A is coming from R power R, B is coming from R power N, and I can invert in that neighborhood. Okay, so next thing is I want a little bit nice description about this, the open neighborhood U tilde. I can just simply use the product topology of R power R cross R power N. So make sure, if necessary, shrink this U tilde a little bit more so that it looks like U cross V, so that U become a neighborhood of A, V become a neighborhood of B. The product topology, I have a basis always containing product of the basis elements, and therefore at around a point I can always make sure that such open sets I can push it in around A. Yeah, so I guess this is there is a technical error if I'm saying that cross product of basis element just to give you a basis. I need again, I think a matrix space or something. In general, I need all open sets. Yeah. Okay, so anyway, this is kind of just follows from just basic point set topology. Okay, so shrinking this U tilde down, I just made sure the function look like f is from U cross V to W. Injectivity again follows from inverse function theorem, and U become a neighborhood of A, V become a neighborhood of B, and W become a neighborhood of A comma 0. Again, remember, I have an inverse, and on the other side I have an open set there. Okay, so the inverse image, I am trying to study how it should look like. Okay, so the secness is again assured from my definition and my statement of the inverse function theorem, so I don't need to bother about that. So only thing is now I should need to find out how does GK explicitly look like. So my fxy is like this, and therefore xy should be equal to g of the point on the left. So what I can do is this particular expression fxy, I can just write it, plug in a z over here, and I am going to recover the function hxz. Okay, so the point is there exists a function hxz which matches this description. That is kind of immediate. Just set z over here and you get something which depends on both x and z. Okay, but now the problem is, how do I make sure my h is nice? In a sense, h should be continuous, h should be ck, and so on. So that just follows from the definition of G, because what hxz is nothing but, if we compose along with G the projection map to the last few variables, you end up recovering your h. And I already know that G is of class ck. Yeah, so this is from inverse function theorem, and the projection maps are basically having the components being those variables. So therefore the derivatives of this are always existing. In a sense, these projection maps are always smooth. It is of class ck for any k. Okay, so if I compose these two, I turn out to get a ck map over here. Okay, so therefore my h turns out to be a ck map. So now I have this open set W. I would try to kind of split it somehow. So this is an open set around the neighbor. It's an open neighborhood of the point a comma 0. Okay, so if it's a neighborhood of a comma 0, again just by using the product topology as I spoke of earlier, I should be able to find out a basic open set which look like open ball around A cross a open ball around 0. Okay, so and the entire thing goes again inside W. So what you would do is that you would pick up this particular B delta A, which is the disk around A, which is the ball around A. Okay, and then I'll do something to define my function G, which is a statement of the theorem. So how do I do this? So remember, my B is like that. This B points of B, if I put in the first coordinate, and if I in the second coordinate I just plug in 0, then that still goes inside W, because B delta A cross 0 goes inside W. This is a neighborhood of 0. Okay, so therefore I should be able to define my G as follows. This is just H of x0. This definition makes sense. So this is kind of well defined. Now, because H is of Ck, my G turns out to be Ck. We only need to check that this H is a right candidate for what we are looking. So what do we seek so far from the statement? Let's see. So I wanted a function G from B to Rn. I have already decided what should be my B. I already have the function being Ck. Okay, so these two are the conditions which I need to ensure that GA equal to B and the function satisfies this equation. This is the most important part of these implicit function theorem. Now GA equal to B again comes almost from the definition. So I know my FAB is A0 because of the definition of capital F. So AB should be G of A0, and G of A0, the way I defined H is G of A0 is same as A comma H A0. And my definition of H is H A0 must be equal to GA. So if I just compare these two coordinate wise, I end up getting GA equal to B. This is part of the condition of the theorem. A similar principle would immediately tells you, so using these calculations, again, each time you apply your F using G and then compare and match the coordinates, you end up getting f of xgx equal to 0. So that's not a surprise. The surprising part is how do we prove the uniqueness? So towards that, let's try to start with another function which is of class Ck defined on B itself, satisfy the given conditions of the theorem G1A is B and these equations. Okay, so if that happens, I want to basically prove that G and G1 coincide. So the best part of doing this, the first thing I should think of is a set T where they are equal, and I want to show that T is equal to B. Right? I want to prove that G and G1 are equal. Let's take the subset of B where these two functions match, and I try to prove that subset is nothing but the entire B. This is where I would do, I have done something already without explaining. So this is what I am going to need. So remember, I have chosen B to be open ball around A. And it's a fact around of topology that this is a connected open set. Okay, so this connectedness of this open set I'm going to use over here. Okay, so this set is T. This set is non-empty because I already know that GA equal to B and G1A is also equal to B. So A is going to be living inside T. G and G1 are both continuous function. Norm is continuous function, which we have seen in the last few lectures. Then the difference set B minus T, I can immediately conclude that this is an open set. So this is a set of all points where G and G1 does not agree. If they don't agree, the norm of their difference should be strictly positive, and therefore this is precisely the pre-image of the composition of norm and G minus G1. from that open set on the real line 0 to infinity. So therefore b minus t turns out to be a non-empty. Okay, b minus t turns out to be some open set. I don't know yet whether it's empty or non-empty. Okay, so if we prove that T is open, I'm kind of done. Because if T is open, then I have T is non-empty and B is connected, and connected topological space, I'm writing it as a disjoint union of two open sets. Well, that's not possible. So therefore, it forces at least one of them to be empty. Okay, so the only way I can do this is make sure that one of them is empty. But T is non-empty, so B minus T has to be empty. So it will immediately establish my T is equal to B. Okay, so that's not too difficult. What you do is you want to show T is open. So you want to prove that any point of T is an interior point. So that any point of T you choose, there should be some ball around that point. Let's say you choose a point W from T. There should be a ball around that point which is also contained in T. Yeah. So you take an arbitrary T, arbitrary W from T, and because my G and G1 both agree at that, then both of them are equal to H of W0, and H maps W0 inside V. Okay. Now, what happens? This means that G1 is a continuous function which maps W to an open set V, somewhere in the open set. Okay. So continuity of G immediately tells me that I should be able to find a open ball around W, so that G1 maps this open ball inside V. Now what does this mean? So if I pick any V from this open ball, I apply my definition capital F to V comma G1 V. This is nothing but that quantity over there. By definition of F, it means f of xy is x comma little f of xy. So this is what I wrote over here. This is my x, this is my y over here. So my f of this is v comma little f applied to this pair of variables. Okay, but now my f vanishes on v. So therefore this is just v0. Okay, if this is v0 and my f taking v comma g and v to that, now we can use g being the inverse function. So that means v1 v comma g1 v is nothing but capital G applied to the pair v comma 0. And then by definition of g, or how we definition of h, how we achieved it from capital G, it's simply equal to v comma h of v0. And now we can simply compare these two these two tuples. It gives me immediately g1v is equal to hv0. But now if g1v is hv0, the definition of hv0 was gv. Sorry, the definition of gv was equal to hv0. So therefore g and g1 both would agree at that particular point. So what did we prove? We proved that on this open ball, these two functions agree. So that means this entire open ball around W is contained inside T. Yeah, so you start with an arbitrary point of T, you found an open ball around that point, so that this open ball entirely contained inside T. So T therefore should be open set. And then I'm done. Okay, so I'm done with this. If there are questions or confusion at any step, please let me know. Hello? Am I audible?
Yes.
Okay. Yeah. Any question? Yeah, thank all of you.
Okay. So claps for Dr. Sarkar. And on behalf of all of us, I thank to Dr. Sarkar for the wonderful lecture and explanation. And tomorrow we will meet with Dr. Sarkar. And also that lecture will be the last lecture of the workshop. And one important announcement. I sent two links. One is feedback form and other is evaluation form. And please fill it. And for the certificate, both forms and attendance are must. So please fill it. And if you have any problem, then please write on the TW group also. Okay, thank you all of you for joining. Thanks.